All right, this is going to be the remainder theorem. What the remainder theorem states is that I can use synthetic division to find the evaluation of a function. So let's say my original function was 6x to the fifth minus 12x to the fourth plus x to the third plus 3x squared minus 6x minus 15, and I wanted to evaluate this at x equals 2. One way I could do this is I could just plug 2 in. Every time I see x, I'm going to plug in 2. That's going to take a little bit of work. I already did that and found that f of 2 equals negative 7. However, what I can do is I can do that with the remainder theorem in synthetic division. So what I'm going to do is I'm going to synthetically divide this out. And what the remainder theorem says is that the remainder here is the same value as where it's defined at. So f of 2 is going to be negative 7. So what that says is that negative 7 is going to appear here, and I can use synthetic division instead of all this work. So let's try it. I'm going to drop the first one, multiply by the number in the box. That's going to be 12. That's going to be negative 12. I forgot that negative sign. So this is going to be 0 because I'm going to add. Multiply by what's in the box. So 2 times 0 is 0. Add. Multiply by what's in the box. And then I'm going to add. So that's going to be 5. Multiply by what's in the box. I'm going to add. Then I'm going to multiply by what's in the box. And then I'm going to add. So do you see how I still got that negative 7? So the next example is I'm going to have 6x to the fourth plus 21x to the third plus 4x squared minus 13x minus 3. So what I'm going to do, I wrote all those coefficients out, and I'm going to put negative 3 in the box, and then I'm going to synthetically divide. So I'm going to drop the first one, multiply by what's in the box. So that's negative 18, add, which is 3, multiply, which is negative 9, add, which is 5, multiply, which is 15, add, multiply, that's negative 6. So that remainder is negative 9. So what I can say is I have f of negative 9, or f of negative 3, what I plugged into the square here, is going to be negative 9. That's my remainder. So that would have been the same thing had I put negative 3 in each one of those x's. The remainder theorem is going to make things a lot easier to evaluate functions, especially at big polynomials. I'm going to move on to the next example. I have f of x is x to the fifth plus x to the third minus 5x squared minus 15x minus 2. And I'm going to evaluate that at x equals 2. So what I'm going to do is I'm going to put 2 in the box. I'm going to find that I'm missing an x to the fourth term, so I have to add a 0 in. So my coefficients are 1, 0, 1, negative 5, negative 15, and negative 2. Drop the first number, multiply by what's in the box, add, 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 multiply by what's in the box, add. So I can say that f of 2, or my evaluation at 2, is negative 12. So when x equals 2, y equals 12. Negative 12. So the big key is to write in any missing coefficients. Last problem is that if f of x equals x to the fourth minus 2x squared minus 2x at x equals -3. So I'm going to put -3 in the box. I'm going to put the coefficients with zeros for any missing. So 1, I'm missing an x to the third, -2, -2, and 0. I've got to keep place. Drop the first one, multiply, add, multiply, add, multiply, add, multiply. That's going to be 69 positive. So when I add f of -3 is going to be positive 69. That is it.